Well, Chapter 7 equates electron configuration to the different trends we have in the periodic table. So, number 4, make a simple sketch of the shape of the main part of the periodic. Make a simple sketch of the main shape of the main part of the periodic table shown. Okay. Ignoring H and E, write a single straight arrow from the element with the smallest bonding atomic radius to the element with the largest. B, ignoring hydrogen and helium, write a single straight arrow from the element with the smallest first ionization energy to the largest. And C, what is the significant observation you can make from the arrows you drew in parts A and B? All right, so the trend on the periodic table is as you go up a group, you increase in ionization energy, and as you go across a period, you increase in ionization energy. All right, so that's how it works. So if you're looking at the hardest atom to take an electron off of, that would be helium. If you're looking at atom size increases as you go from. I guess we get to go from right to you're going from right to left across the period, and atom size increases as you go down a group. So cesium would be a big puffy atom, and helium would be a really tight small atom. So the trend here is as the radius, the size increases, the first ionization energy decreases. So big puffy atoms like cesium are easy to take an electron away from than tight little atoms like helium. In a chemical process called electron transfer, an electron is transferred from one atom or molecule to another. We will talk about this extensively in Chapter 20. A simple electron transfer reaction, A reacting with A to make A plus and A minus, in terms of ionization energy and electron affinity of atom A, what is the energy change for the reaction? For a representation for a representative nonmetal such as chlorine, is the process exothermic. For a representative metal such as sodium, is this process exothermic. All right, so ionization energy is knocking electrons off of atoms. This is always endothermic. I know we talk about sodium being so reactive it wants to give up its electron. It doesn't want to give up anything. It's trying to hold on to its electron. It can't when something like it reacts with chlorine. When an atom takes an electron, it is always exothermic. All right, so there's an attraction between the protons in the nucleus and an electron, so it's always a releasing process. So ionization energies are always endothermic, and electron affinities are always exothermic. What is meant by the term effective nuclear charge? All right. How does effective nuclear charge experienced by valence electrons of an atom vary going from left to right across a period on the periodic table? All right, so in order to understand effective nuclear charge, we have to understand what the relationship is in terms of electron configuration. So if we look at the first element in the second period, it's lithium. We have two inner electrons and one outer electron. All right, so the inner electrons are called core electrons. The outer electrons are called valence electrons. All right. The way this works is the interaction between electron and electron is repulsion. So core electrons block outer electrons from feeling the protons in the nucleus, which are trying to pull that electron in. All right, so inner electrons block the outer electron, the valence electrons from feeling the nucleus. The more protons you have in the nucleus, the greater the attraction between the outer electrons and the nucleus. So it's a push versus pull, right? How many core electrons do you have blocking the valence electron, and how many protons in the nucleus do you have pulling on that electron? So when we go across the second period, right, we go from lithium to beryllium, we haven't changed the core electrons. We still only have 2 core electrons blocking the outer electrons from filling the nucleus. What we have done is put more protons in the nucleus. So we're getting more of a pull on that outer electron. So I'll just flick back to show you the effect here. 3 protons pulling. I got a skinny little line, right? So I've got a certain amount of pull on that outer electron. With an extra proton in the nucleus, we get even more pull on the outer electrons. 5 protons, even more pull. 6 protons, even more pull. So as we go across the period and we get more and more protons in the nucleus, without changing the core electrons, we get a greater pull on those outer electrons, and they're harder to take off. We increase in ionization energy. Harder to knock those electrons off of the atom. So as the number of protons in the nucleus increases and the number of core electrons remains unchanged, effective nuclear charge increases. All right, so effective nuclear charge, again, is how hard an atom pulls on its electrons. Increases going across a period.